My name is Professor Guillaume Key Paik. I am Professor of Marine Technology in the Department of Mechanical Engineering at University College London. In this video, I will summarize the key findings from our supercomputer-based simulations that digitally reconstructed the final hours of the Titanic's sinking. The Titanic sank in the North Atlantic Ocean on 15 April 1912 after colliding with an iceberg on its starboard side. The impact occurred at 11:40 p.m. ship's time on 14 April, and the vessel sank approximately 2 hours and 40 minutes later at around 2:20 a.m. Out of 2,224 passengers and crew, more than 1,500 people lost their lives. The scale of this disaster left a deep impact on society and raised fundamental questions about ship design, safety, and emergency preparedness. In 1985, the wreck of the Titanic was discovered about 370 nautical miles south-southeast of Newfoundland, Canada, at a depth of approximately 3,800 meters. In recent decades, advanced deep-sea technologies such as remotely operated vehicles, submersibles, and 3D photogrammetry have enabled detailed surveys of the wreck site. For more than a century, the sinking of the Titanic has been studied through eyewitness testimonies, official investigations, and forensic surveys of the wreck. Despite these efforts, several fundamental engineering questions have remained unresolved. What exact damage did the iceberg inflict on the hull? How did flooding propagate through the ship over time? What structural failure mechanism led to the hull breakup? And how might the outcome have differed if the ship had experienced a head-on collision rather than a glancing side impact? To address these questions, the UCL research team carried out the most comprehensive physics-based digital reconstruction of the Titanic's final hours to date. This project was led by me and commissioned by Atlantic Productions in 2025. The work was undertaken together with my team members, Hyung-Jin Kim, a PhD student at UCL, and Mr. Brian Thomas from Thomas Naval Architecture in New York. The results of this project were featured in the documentary Titanic, The Digital Resurrection, first broadcast by the BBC and National Geographic in 2025 to mark the 113th anniversary of the disaster. As the principal investigator, I participated in the filming together with Dr. Simon Benson and Dr. Stephen Payne, under the direction of Atlantic Productions in London. The full scientific outcomes of this work have been published as an open access paper in the journal Ships and Offshore Structures. To digitally reconstruct the sinking of the Titanic, we first needed to build accurate three-dimensional computational models suitable for structural and flooding simulations. This required extensive manual digitization. The original ship drawings were available only as early 20th century blueprints, not modern CAD files. Our team carefully traced and reconstructed the ship's geometry by hand, followed by rigorous verification to ensure geometric accuracy and realistic material properties. This pre-processing stage was essential. Without accurate geometry and material modeling, reliable numerical simulations would not have been possible. Equally important was defining realistic collision scenarios between the Titanic and the iceberg. The speed, angle, and location of impact strongly influence hull damage and the subsequent sinking process. To establish scientifically credible input conditions, we reviewed extensive historical evidence. This included eyewitness testimonies from the US Senate hearings and the British Board of Trade inquiry, as well as modern forensic and engineering studies. At departure from Southampton, the Titanic's draft was recorded as 10.26 meters forward and 10.46 meters aft, indicating a near fully loaded condition. By the time of collision, some coal, fresh water, and provisions had been consumed. We therefore assumed a reduced draft of 9.37 meters forward and 10.29 meters aft, corresponding to an estimated displacement of 48,300 long tons. At the time of impact, the ship was traveling at approximately 22 knots. The iceberg was sighted by lookout Frederick Fleet, who rang the warning bell and reported "iceberg right ahead." First Officer Murdoch ordered evasive maneuvers, including hard starboard, followed by engine commands. The estimated collision angle between the ship's longitudinal axis and the iceberg face was approximately 15 degrees with initial contact near the forepeak tank. Eyewitness testimony from Frederick Barrett, the leading fireman on duty in Boiler Room 6, reported that a hole appeared approximately 2 feet above the stokehole plates. This observation was used to define the vertical location of the hull damage in our simulations. The total contact duration between the hull and the iceberg was calculated as approximately 6.26 seconds in the simulations, which agrees well with eyewitness estimates of 6 to 7 seconds. The resulting hull breaches were concentrated within a narrow longitudinal strip on the starboard side, extending across 6 watertight compartments, from the forepeak tank to the aft bulkhead of Boiler Room 5. Most individual breaches were relatively small. Many were smaller than the size of an A4 sheet of paper. The total simulated breach area was approximately 1.7 square meters, about 1.5 times larger than the estimate previously made by Edward Welding, a senior naval architect at Harland and Wolff. Although the breaches were small in size, their distribution across 6 watertight compartments made progressive flooding unavoidable. This longitudinal spread, rather than the size of individual holes, was the key factor leading to the loss of the ship. Flooding began immediately after the collision. The Titanic was equipped with 5 ballast pumps and 3 bilge pumps, providing a theoretical maximum pumping capacity of about 11.4 tons per minute. In reality, pump performance was severely limited by falling steam pressure and by discharge outlets becoming submerged. By comparison, our simulations show that the average flooding rate during the first hour was approximately 243 tons per minute, more than 20 times the maximum pumping capacity. By 113 minutes after the collision, 6 forward compartments were fully flooded. At this stage, the boat trim had reached about 4.5 degrees. After this point, the trim increased rapidly, leading to a catastrophic loss of buoyancy. As flooding progressed, the weight distribution along the ship changed significantly. Floodwater added weight to the forward part of the vessel, while buoyancy was progressively lost at the bow. This imbalance generated rapidly increasing hogging bending moments along the hull girder. At 158 minutes and 36 seconds after the collision, the trim angle reached approximately 14.35 degrees. At this moment, the maximum hogging moment occurred near the aft expansion joint, initiating the first global hull girder collapse. Before global collapse, local structural failures developed under increasing hull girder loads. The bottom structure experienced high compressive stresses, leading to buckling, while the deck structure was subjected to tensile stresses, causing yielding and tearing. These local failures reduced the effective stiffness of the hull girder and accelerated the global collapse process. The hull girder collapse at the aft expansion joint occurred at a trim angle of 14.35 degrees. Once the critical hogging moment was reached, structural failure progressed rapidly. First of all, deck structures fractured in tension, producing visible tearing of the superstructure, and then bottom and inner bottom structures buckled and crushed under compression. Finally, the failure propagated both vertically and longitudinally, leading to a clean breakup of the hull. These simulated events are consistent with eyewitness accounts, including reports of funnel collapse and the observed breakup location near the aft expansion joint. The Titanic sank following a glancing side collision with the iceberg. Although the ship narrowly missed the iceberg, the resulting side damage extended across 6 compartments, making the vessel unsalvageable. This raises an important engineering question. What would have happened if the Titanic had struck the iceberg head-on, possibly at a reduced speed? In maritime engineering, side collisions typically produce longitudinal damage along the hull, while head-on collisions concentrate damage at the bow. Our simulations indicate that even at full speed, a head-on collision would likely have confined damage to the forepeak tank and holds 1 to 3. In that case, the watertight bulkheads would probably have prevented progressive flooding, and the ship could have survived. At lower collision speeds, the damage would be even more limited, further increasing the likelihood of survivability.